Hello and good morning, CTS265, Section 840 students for the Fall 2016 semester at Anne Arundel Community College. This morning's video tutorial is going to be on Discovery Activity number 3, where we're going to be taking a look at the EIGRP Topology Table, and we're going to start to talk about terms such as reported distance, feasible distance, one that is not mentioned in the lab but is very, very important, which is the computed distance. And we're going to differentiate the computed distance from the feasible distance because it's extremely important that you understand that a lot of material you'll see refers to the computed distance as the feasible distance, but that is not the case. We're going to talk about successors, feasible successors, and finally that feasibility condition, which is the condition that must be met in order for an EIGRP route to be considered a feasible successor. All right, so step 1 of our lab basically is going to have us kick off some debugs here on the branch router. So let's get onto the branch router and go from user exec to privilege exec, and we're going to say debug EIGRP packets. And when we're debugging EIGRP packets, you can see the output we get below is an indicator that we are debugging literally every single EIGRP packet: the update, request, query, reply, hello. So we've got quite a bit, so this is going to generate quite a bit of output. So let's get into global config, where we're going to say router EIGRP 100 and hit enter. And we're actually going to enable EIGRP on the Loopback interface. Do show IP interface brief. It looks like the Loopback and Ethernet 00 interfaces. So if we go back and take a look at the topology, we're doing the Loopback interface here and only the Ethernet 00 interface here, which is going out over WAN link 1, right? So let's get back on the branch router, and we're going to say network 192.168.1. Now you'll notice the loopback address shows 192.168.1.1. Excuse me, that's probably a /24, but we're going to make sure that we are extremely precise in our activation of EIGRP. So 192.168.1.1, and we'll put the quad zeros at the end of it. So if I were to say do show run section EIGRP, that's what we have right now. Remember, that quad zeros means that exact IP address. So we're forcing it to match that exact IP address. And again, we don't see any output right now because it's our loopback interface. And so EIGRP is smart enough to know I'm not going to establish an adjacency on my loopback interface with anyone else. Therefore, there's no need for me to generate packets. However, when we say network, and actually let's take a look here at do show run interface Ethernet 00, it should be a /30. It is. So we'll say network 172.16.1.2. And we need our wildcard mask in here. And so the wildcard mask, again, is the inverse of the subnet mask. So if we were to subtract that from the all 255s, we would end up with 0.0.0, and then 252, or I should say 252 subtracted from 255 is going to leave us with 3. Now this should start to generate some output. As you can see, we're going to get quite a bit of output here. So let's go ahead and say you all to turn off all possible debugging, and then let's scroll back up to the top. So again, what we want to pay attention to here is we'll notice that right away we have hello packets that are going to be generated, and we can see those up at the top here. And let me the ink2go is once again in the background. So let's quit ink2go and then let's start ink2go. All right, so we can see right away EIGRP is sending a hello on Ethernet 00. Now remember, hello packets are not reliable, right? So in terms of expecting a response back, we're not going to expect a response back, and we can tell that when we see this sequence 00. So hello packets are sent unreliably, which means they're thrown out there on the wire. If they get to where they're going, great. If they don't get to where they're going, okay. You know, I'm not going to get a reply back that tells me, hey, I never got that hello packet. So you can see we're also receiving hellos on Ethernet 00, and we're receiving them from the neighbor 172.16.1.1, and that's going to be the HQ router. Again, no sequencing information on the hello packets that are being sent out periodically every 5 seconds by default, again, depending upon the medium. And you can see here ours are, where are we at? Looking for the next hello. I may have to scroll down a little further because there was quite a bit of activity here. So we should send our next hello at 14:23:28, or right pretty close to 28. So now the next thing that goes out, you'll notice that you see that we are in-queuing an update message, right? The neighbor adjacency has come up, right? So we receive an update message from the neighbor, and you can see unreliable, reliable. So we've received one reliable message, which is going to be this update message, because updates are sent in a reliable fashion. Okay, and when we come down here, you can see the flag where we have the sequence number is no longer 00, it's 10. And so we're getting that sequence information telling us that we've got a reliable packet. Now, when we receive a packet that's being sent reliably, we must respond with an acknowledgement that the packet has been received. And then you can see that we have the unreliable, reliable again. It's for sequence number 1, which is that update message which we received earlier. And then you can also see here it starts to increment, where sending an update, sequence number 2. And so then we should receive an ACK back. And here it is down here. Again, a lot of output here. You just kind of have to make your way through. And you can see right there that we get that acknowledgement back. I went over the 2. That's the number 2 there. But again, when you send something out reliably, there's going to be a sequence number, and you would expect to receive something back. So in the debug output, it's a little challenging at times to sort of follow what's happening. If we were to take a look at Wireshark, and let me go ahead and kick off a packet capture here, and we're going to take a look between router 8 and router 9. So if I say show run section EIGRP on router 8, you can see that we've got that network statement. So any interface that I bring up is immediately going to cause EIGRP to send an update message out. And so let's see, because remember we said you have to get an acknowledgement. Well, what kind of a message is being used for the acknowledgement? And you're going to see that it's a hello message. So let's go into global config, and we'll say interface loopback 88. And yes, you guessed it, we're going to say 88.88.88.88. And we're going to make it a /32. Now, as soon as I do this, we go back to the packet capture and take a look. Let's stop that right there. Perfect. All right, almost perfect. So right here, sorry about that. Let me get this to settle down. There we go. So what takes place? So as soon as I entered in that loopback address, we had EIGRP activated, and unfortunately that is red, so I'm going to go with green here. So here is where we hit enter when we had the 88.88.88.88. I'll just call it the 88 network. Then we send out a multicast packet to the EIGRP multicast address, 224.0.0.10. You can see the protocol is EIGRP. Remember, it's protocol number 88. And it is an update message. We then see router 9 is the source sending something to router 8. And what does that happen to be? Exactly. It's an acknowledgement, because the update message is reliable. It's sent reliably, meaning when this update gets fired out, I am expecting some sort of an acknowledgement back, and then I get it right here from router 9. But then what do you see? Exactly. So we see this other exchange here where router 9, who has just learned new routing information, and again, he's going to do exactly what EIGRP is trained to do, a triggered update. And there it is. Something in router 9's EIGRP topology table has changed. So it is going to trigger an update message, and router 9 is now going to communicate to anybody who's out there listening to EIGRP, right, to this EIGRP multicast address. He fires it out there on the wire and says, hey, I just learned some new routing information. Here's an update message. And then what does router 9 receive back from router 8? He receives an acknowledgement. And again, it's a hello packet, but it's being sent to acknowledge reliable update messages, right? Or messages that are being sent reliably, that it's the hello packet. So let's dive in to the hello packet real quick, or I should say, first let's take a look at the update. So here's the update message, and what is it? Prefix length of 32, the destination is the all 88s, and so again, this is nothing more than our update message for this new network. So then we get this hello. So if we take a look at the hello, all it is an acknowledgement, right, with a value of 4 to indicate that it's an acknowledgement. What autonomous system number are we using? Autonomous system 1. And you can see the operation code is the hello message, but it's an acknowledgement within that hello message. And then we see the update that 9 sends out, which is what? Yeah, hey, that I just learned about this network, the 88 network. And what is router 9 also passing along? You can see, and I love this when you look at the packet captures here in Wireshark. It's actually, I'd be curious to see what it does if we were doing the 64-bit named mode. But take a look at that. It's smart enough to recognize that this is the classic mode, the legacy metric. So you can see that the delay is scaled, and that is the max value there. We've got the bandwidth, scaled bandwidth. It shows the MTU. And remember, a quick word about MTU is even though it is communicated with the updates, and this is actually fortunate that we run into this, MTU is not used in the composite metric calculation. It is not used, right? You'll see in some older text where it says that MTU is some sort of a tiebreaker of some kind. I believe actually our text may mention that. But MTU is not used in the composite metric calculation. And we'll talk about the tiebreaker scenario much later on. You can see that it shows hop count, right? It's actually giving us the hop count. We get the reliability. We get the load. If there was a route tag, we would see that there, and then some flags, and then the next hop value of the quad zeros. So again, it's actually, Wireshark is smart enough to catch that this is the legacy metric, not the 64-bit metric, and then we get that final acknowledgement message. And so these are the conversations that are taking place, and then you'll notice that that was it, right? So that was the end of the exchange. But again, that update was sent out reliably. We get an acknowledgement back. Router 9, who now has new routing information that he just acknowledged, and he acknowledged it how? The acknowledgement, is the acknowledgement sent as a multicast or unicast? Exactly. It's being sent as a unicast back because we want to make sure that we're just responding back to the individual who sent the reliable packet, router 8. So 9 directly sends it as a unicast back to 8. It wouldn't make sense for 9 to fire it out as an acknowledgement. It wouldn't make sense to fire it out as an acknowledgement to everybody via multicast. And so we also see our sequence number, right? So when this update went out, you can see it goes out as sequence 4 in the first update. We look at the acknowledgement, and we're acknowledging 4, right? So that's that value I was talking about. So this is the number that you're seeing. So the sequence number is 4, so it would be that 4/0. The acknowledgement is for I'm sorry, went one too short. The acknowledgement is for sequence number 4. And then router 9 sends out an update, right? That goes out as sequence number 4. And then what is the acknowledgement? I'm acknowledging that the sequence number 4, your update, which was sequenced with number 4, this is the acknowledgement packet coming back saying, yeah, I got 4. And the reason that it acknowledges that specific packet is router 9 could be generating at this point, hundreds of update messages possibly. And so when he sends those update messages out, he needs to make sure he gets acknowledgments back for those specific update messages. All right, so that's a nice deep dive look at what exactly is taking place in those debugs that we're seeing. And again, you get a much nicer picture here in the Wireshark packet capture. So let's transition back to the activity. And again, you could see, EIGRP received acknowledgement. And there's our sequencing information, right? Those sequence numbers. Okay, so we're on the branch router. And now what we're going to do is we're going to take a look at show IP EIGRP traffic. And you can see, remember, hellos are being sent every 5 seconds. So that number is going to update every 5 seconds. You can see we've got updates sent and received. We've sent 4, we've received 3. And then the same thing with queries, replies, acknowledgments sent and received. And then we get the process ID numbers and the protocol dependent module process ID. And so again, if I were to run that command right now, you can see that the hellos are always going to increment. Now, if you see a ton of incrementing and you're not anticipating that there were changes in your environment, and these updates sent and received are changing, and the queries sent and received are changing, as well as the replies, then you probably want to investigate things. There could be some issue in your environment. All right, so now let's transition on to step number 4. So we're going to take a look at the routing table on the branch router. So we'll say show IP route, and I'm going to trim it down to EIGRP. And so here's where we're going to start our conversation of how EIGRP, or why EIGRP selects the specific routes that it does. So now when we take a look at this, the first thing we want to talk about is the D. And the D represents EIGRP. And why do you think they chose the letter D? Well, we see that they use EX for EIGRP external. It doesn't look like E by itself is used. E1 is used, but that's OSPF. E2 is OSPF. And I don't see E being used in here anywhere. So again, they chose D because D stands for dual, the diffusing update algorithm. And this is what EIGRP relies on in order to provide loop freedom throughout the entire EIGRP domain. And it stands for the diffusing update algorithm. And we're going to talk in a second here about the creator of this. It's a gentleman by the name of J.J. Garcia Luna Aceves. And we'll take a look at some early papers that he had written on the diffusing update algorithm. And basically what dual is doing is dual guarantees that you have mathematically guarantees a loop-free path. And when we get into the reported distance and the feasible distance and the computed distance, you'll see what we're talking about. And so DEX is just indicating that this is external EIGRP information. Again, the administrative distance for EIGRP internal information is 90. For external information, it's 170. And now we come to this value right here, which is commonly referred to as the feasible distance, right? You'll see this referred to as the feasible distance in a lot of publications. However, this number, while it can be representative of the feasible distance, is not the feasible distance. It is the computed distance. And what I mean by that is the feasible distance is the metric when the route last transitioned from active to passive. However, right, so when the information, when the route goes from an active state, which means there's a dual or there's a computation being done to determine the metric, right, that composite metric for that route, it goes into the active state. Once it has been resolved, right, and completely calculated, it goes into the passive state. When we look at the topology table, we'll see the letter P next to the routing information, showing that it is converged, right? That routing information is in a passive state. And so for the feasible distance, it's the last time the route went from active to passive, and then we get some sort of a metric number, and I'll use 409,600. Right? So that is the feasible distance number, and it actually is called out in the topology table. It says FD is, and it gives you the value. However, feasible distance is a point-in-time snapshot, and it's the point in time specifically is when that route went from active into passive, boom. We get a snapshot of the feasible distance, of the metric. That is the feasible distance. However, at that exact moment, this value, the computed distance, is also the same as the feasible distance. But if there's a change in the topology that doesn't cause the route to go active, but yet changes the value of the computed distance, you will see this value will change, and the feasible distance will still show the value that was calculated the last time that route went from active into passive. In other words, this is a static value. It is not a dynamic value. The computed distance is the dynamic value, and the confusion between these two values comes into play because initially they are the same. As soon as the route goes from active into passive, the computed distance and feasible distance report the same value. And so that's why a lot of times you'll see individuals say, oh, here's the feasible distance. In fact, I believe in the Cisco Networking Academy curriculum, in the CCNA curriculum, they actually specifically call out that that is the feasible distance. And it is not. That is the computed distance. And we'll do a little experiment where I will change the delay just enough to have the metric, right, the computed distance will change. However, it won't force it into an active state. Therefore, the feasible distance stays the same, but the computed distance is going to change, right? So very, very important to note that that is the computed distance. That second number there after the administrative distance, that is our computed distance. Okay, so now what we're going to do is on the branch network, we're going to go ahead and bring up everything else in terms of starting EIGRP on those other interfaces. So show IP interface brief. We're going to get into global config. We're going to say router EIGRP 100. And now we need network statements in there for the .2 and the .3. So 172.16.2.0. And again, we've got a /30. So this is going to be a .3. And then simple change here. Our adjacency is up. And our adjacency is up on the .3 interface. So now do show IP EIGRP neighbors. Let's see what we've got. So again, you can see that the medium here is definitely not or I should say, not a slower than T1 connection. So we're faster than a T1 connection. We can tell that with the hold time, right? The hold time is clearly 15 seconds. Remember, the hello time is 5 seconds. The hold time is 3 times the hello time. If this was a slower than a T1 and on a NBMA network, non-broadcast multi-access, we would see what number here at the maximum would be right around 180. And then the hello time is 60 seconds. So again, we've got a hello time here of 5 seconds, a hold time of 15 seconds, and all of the adjacencies are up. And I'm actually receiving, do show IP route, EIGRP, I'm actually receiving just that one, or at least in the routing table, I'm only showing that one route in the routing table. And remember, this is the global rib. EIGRP has a neighbor table, which was that do show IP EIGRP neighbor. So this is the neighbor table. This is the global rib. And now we're going to take a look at the third table EIGRP uses, and that's going to be the topology table. And we're going to see how dual calculates the best path to a destination. So the topology table is just do show IP EIGRP topology. And here is the topology table. So a quick look at the topology table shows us that the state for, and I guess I can circle or square these all up here, the state for all of the routes in the topology table is passive, and this is a good thing, right? If everybody is passive, that means that I don't have any calculations taking place, that everything from a route perspective is converged. Now, you can see we have the routing information listed here, right? So for each of these routes, there's that 30, there's for the 192.168.0.0, the 1.0, 172.16, so there's our point-to-point connections. Now, you'll see that it says one successor, and then here, the feasible distance is 537,600. Now, you may be tempted to look over here and say, aha, that's the feasible distance in the output that we're looking at. It is not. That column, and I'll draw it from right here, this column, or I shouldn't say this column, but the first number that is reported prior to that forward slash, that is the computed distance. It just so happens, remember, these routes just went from active to passive. Therefore, the feasible distance value is the same as the computed distance value because there haven't been any change, or I shouldn't say any changes, but any changes, any adjustments to the computed distance. But if we were to go manipulate the delay, you'll see those numbers right there can be or will actually change, and the feasible distance will stay the same. Remember, that feasible distance number is not going to change until and if and when this route goes into the active state and then back into a passive state. That is the only condition under which that feasible distance value is going to change. But the computed distance value here, that can be changed. We can manipulate the delay and cause that number to change. So keep that in mind. Let me clear this out here. So now you'll see we have one successor, right? But you'll notice we have two paths that show up here, one of which is the successor. So we know that that's the computed distance. So then what is that value here? What is the second value after? I'm sorry, I didn't mean to line right through that. The second value after, I just like having some issues here with the pad. Let me go just grab a little larger piece of real estate there. And so that second value, that is the reported distance. In other words, that's the distance value that's being reported to the branch router from each of these routers. So or I should say across each of those links. So the link 172.16.11, 172.16.21, the reported distance is the same, right? The reported distance shows up as the same. And so what ends up happening is we have one successor that's been chosen, but there are two possible routes. If we come down and we look here, we see the same thing. And you also see again that reported distance, the reported distance from 1 and from 2, from these links to the branch router is the same. And then these point-to-point links here, you can see these are connected via loopback addresses, but we still get the feasible distance, right? And actually, I'm sorry, the loopback was, where was this? Was the loopback here. This is the serial interface and the Ethernet interface. All right, so let's go ahead and let me make sure that was everything. We talked about the passive. We talked about the reported distance, the feasible distance, the computed distance. And again, there's a note here in the lab. It says the best path to the destination is based on the lowest total cost of the destination. The best path is selected as the successor route, and the value of the total cost for the successor path is selected as the feasible distance. And remember, that's the feasible distance. This is the computed distance. Okay, so not all of the possible paths. You'll notice we've got 3 connections. If I come over to the diagram here, you can see the branch router has Ethernet 00, Ethernet 01, but then a serial interface as well, right? So it's got these 3 WAN links. And so when we talk about the reported distance, what we're saying is that this is going to send in a reported distance. So it's going to say, hey, the distance to get to the prefix you're trying to get to, if it's this 192.168.0.0, hey, I'm reporting to you that my distance is X. And the same thing over WAN link 2. WAN link 2 is going to say, hey, my reported distance, my reported distance is X to get to that prefix. And then the same thing is going to happen here. So the reported distance is from the perspective of the neighbor, right? Being this WAN cloud is reporting back that, hey, my reported distance based off of the bandwidth and delay and me doing the composite metric calculation, that my reported distance is X as well. So the feasible distance is from the perspective of the branch router. So whatever the branch router's cost is for that link to the neighbor reporting the reported distance. So again, to simplify this, branch router is going to take in 3 reported distance values. And so we're going to say it's going to be reported distance value 1, reported distance value 2, and reported distance value 3. And again, the reported distance is from the point of view of the neighbor to the branch, the neighbors of the branch router. The branch router takes in those 3 values and then says, okay, well, neighbor 1, neighbor 2, and neighbor 3 are telling me that this is their reported distance to get over to that network. Then, in order for the branch router to calculate its feasible distance, it's going to go ahead and say, let me take reported distance 1, reported distance 2, and reported distance 3. I'm going to add my cost to get to them, to each neighbor. And that is what makes up the feasible distance value and the computed distance value. Because remember, those initially are the same. And so again, the branch router takes in the 3 reported distance values from the neighbors, whatever they are reporting their distance to be, to get to that network. And then the branch router says, okay, what is my cost? What is my metric? What is my cost to get to that neighbor who reported their distance to me? And then once those values are hashed out, the branch router then says, all right, which one is the lowest. And then that is going to be my successor route. And then there will be a successor router, right? So WAN link 3, WAN link 2, WAN link 1, one of them could be the successor. And then we end up with the feasible successor. And the feasible successor, and we talk about the feasibility condition, the feasible successor, think of it as a standby route, a backup route, right? And we're going to get into the feasibility condition. What condition has to be met for a path to become a feasible successor path? But we'll get to that in a second here. So again, we saw the topology table on the branch router. If I say do show IP EIGRP topology, excuse me, and again, we kind of have this special case here where the reported distances are the same, and therefore they both show up here in the topology table, right? Now, obviously, we're not seeing all of the links. So where is 172.16.3.1? It's not here, right? Now, it's not that it is not, and let me double negative here. It's not the case that the path via 172.16.3.1, it's not the case that it's not in the EIGRP topology. It is in the EIGRP topology table. However, in order to see that value, we have to say topology all links. Because show IP EIGRP topology all links, that is going to show me every single possible path that I have, irrespective of whether or not that path is a feasible successor. And so what can we take away from the running of these two commands? Show IP EIGRP topology is only going to show me the successors and any feasible successors that might be in here, right? That is what it's going to show me. And again, that's the show IP EIGRP topology. So if a possible route, or I should say a possible path, doesn't meet the feasibility condition to become a feasible successor, you are not going to see the output in the show IP EIGRP topology command. Again, it might not show up here, but it's definitely going to show up in the EIGRP topology table. We just need to coax it out of there by using this option, show IP EIGRP, show IP EIGRP topology all links. So again, I'm saying show me everything, even if it's the crappiest, worst route, and I would probably never consider it. It doesn't meet the feasibility condition. And you can see just by looking at the metrics here, it's like, wow, that is brutal, right? 256 million for the reported distance, and the computed distance, right? Remember, that's the computed distance. And this is also a great way to demonstrate the feasible distance is 537,600. There's the computed. You can see these values here. Those are not feasible distance values. Remember, those are the computed distance. They are different than the feasible distance. So that first number, this is a great demonstration here, that first number, while it may be the same as the feasible distance, is not. It's the computed distance, and it's different. You can see how much different it is here. So again, take a look at those values for this path through WAN link 3. It is ridiculously high. And so now this is going to lead us to the discussion of the feasibility, I'll say FC, for the feasibility condition. And in order to become a feasible successor, you must meet the feasibility condition. And what the feasibility condition states is that in order to be a feasible successor, the reported distance must be less than the feasible distance of the current successor. So the current successor is always listed first. So this is our successor, and the successor is typically a router, right? It's a 172.16.1.1, this neighbor. This is the successor route, right? And this is the successor. And the feasible distance value of the current successor is what? 537,600. So if the reported distance from another neighbor, and we'll look at WAN link 2, router 2, if the reported distance is less than the feasible distance of the current successor, you have met the feasibility condition. And I guess in layman's terms, it would be if this second number that's being reported here is less than the feasible distance that shows up right there for that successor route, then you, sir, are a feasible successor. Okay? So when we look at this value, so we'll come down, it actually doesn't show. Yeah, we'll look at it through here because we got a mess up there. So when I look at that value right there, and again, this is kind of a very contrived setup here, but when I look at the reported distance, and when I say when the branch router, from the perspective of the branch router, he receives that reported distance value from router 3 for that successor route. And again, remember, that's that segment that's over there behind the branch, the headquarters router. The branch router compares that value, this reported distance value, to the current successor's feasible distance and says, in this case, is the reported distance less than the feasible distance of the current successor? And so in this case right here that we're looking at, we're saying is 256, 000, 000. That's my test. Is it less than 409? Is it 600? Yeah, 409,600, 409,600. That's the test. If this is true, then it's a feasible successor. If this is not true, it does not meet the feasibility condition and will not be installed in the EIGRP topology table as a feasible successor. And again, I stress that. I'm saying it won't be installed in the topology table as a feasible successor, but it is in the topology table. Again, it will be installed in the EIGRP topology table. It just won't be installed as a feasible successor. And what that means, again, is that it's installed in the topology table. It's not a feasible successor, and then so in order for me to see it, I need to say show IP EIGRP topology all links. And again, those are very, very critical concepts. Being able to compare and contrast the show IP EIGRP topology output against the show IP EIGRP topology all links output. Again, both of those commands are showing me information from the EIGRP topology table. The difference is that when I use the all links option, I will see every possible path, every possible route, irrespective of whether or not those routes would qualify as feasible successors or not. Okay? So again, keep that in mind. I know, and this is, as you can see, the comment I made in class when we were talking about RIP is once we get into EIGRP, chances are you're going to be asking me, can we please go back and just stick with RIP? Because EIGRP becomes far more complicated, far more complex in terms of how it's making its decisions, and then when it is making the decisions, we have routes that are being installed as feasible successors, and then we have other, I should say, we have successors, right? The successors being the routers. We have the successors that are being installed as feasible successors. Then we have other successors who are not being installed as feasible successors. And we need to understand what test it is that's being done to determine who's a feasible successor and who's not a feasible successor, and which values am I supposed to be looking at to make that determination. Okay, so we've exhausted that topic, but again, I can't stress how critical it is to be able to differentiate between the output of the two commands. It's pulling the information from the same table, the EIGRP Topology table, but it's giving you a different view, and it's giving you different information with respect to those tables. All right, or with respect to that table. So step 9, we want to kick off a continuous ping here, and we actually had some issues with this last year, so I'm hoping that we don't run into the same scenario again. So it wants me to ping 192.168.0.1. Now remember, this is the IP address that sits behind, it's this LAN segment, the loopback, right over here. So 192.168.0.1 is that segment. So do I have connectivity? I do. And we know that we have connectivity because if we say do show IP route, EIGRP, you can see that we have learned from EIGRP, right? We have learned the route to get to that network. And it's via 172.16.1.1. So it's going to take that top WAN link 1 path, right, out Ethernet 0.0. And that's how we're getting there. So I'm going to do a continuous ping now. And I'm hoping that this does not, it says 1,000, but we need to transition to the HQ router, because what we're going to do is we're going to shut the HQ router's Ethernet 0.0 connection down. And so let's take a step back. What are we doing here? So I'm going to kick a continuous ping off here. We know the current path that's going to be taken is the path that goes this direction to get to that network. I'm going to shut that interface down, therefore blocking, right, or killing this path. But the reason we're doing this is to show that we have a feasible successor. And our feasible successor is WAN link 2, the router that we're connected here. There's a router right there. We can't see it, but it's there. And we're connected to that router. He is going to be our feasible successor, and we are auto-magically going to install that feasible successor into the global RIB. And so again, remember I said the feasible successor, think of it as like a backup route. So that if my primary path goes away, I don't need to do a complete recomputation of the remaining paths. I already know that that is a loop-free path because it's a feasible successor. And again, that feasibility condition, and this is where the mathematical part of things comes into play. When we're looking at this, the reason that that got installed into the routing table or into the EIGRP topology table, make sure I'm clear there, the reason that this is installed in the EIGRP topology table as a feasible successor is because mathematically, using the dual algorithm, EIGRP has been able to compute mathematically that this is a loop-free path due to the fact that the reported distance is less than the feasible distance going that way. And in layman's terms, in English, mathematically, what I'm trying to say is if the reported distance from WAN link 2 is less than the feasible distance of the current successor, so going this way over WAN link 1, what that mathematically means is it's impossible that there is a loop. Because if this value here, which is x, is less than y, and that's a terrible y, is less than y, it is mathematically impossible that there is a loop in the topology. That somehow, if I went through x, that I would end up then coming back and going through y. And that's why if x is less than y, it is a mathematical certainty that there is no loop going through x. I'm not going to like loop back around and then come back through. It's not going to happen. And that's how EIGRP, using the diffusing update algorithm, says, yeah, this is a feasible successor. And since it's a feasible successor, I'm going to save myself a whole bunch of time in having to sit here and then compute if that link went away, or I should say, this link goes down and the path goes away. EIGRP says, no. I'm not going to then compute, recalculate that path and recalculate the metric for this path and then try to figure out which path is the best path and then install that into the global rib. EIGRP says, no. I already mathematically know that this is a loop-free path, because the reported distance is less than the current feasible distance. Therefore, I'm going to stick them into the topology table. I'm going to call it a feasible successor. And if my current successor goes away, right, boom, I am going to dump that into the global rib within milliseconds, to make sure that we are not dropping tons of traffic. And again, EIGRP is simply saving tons of time, or I should say theoretically what could be a lot of time from a traffic redundancy perspective or a throughput perspective. I'm saying I'm saving a lot of time because I don't have to sit here and recalculate all these other paths, right? I already know that if WAN link 1 goes away, then WAN link 2 is my backup alternative path that has already been calculated to be loop free. All right, so let's jump onto the branch router. We're going to say repeat. I'm going to say 10,000 here, and I make sure it doesn't. Yeah, the problem we had was when we kicked this off, I believe it's going to stop, or there's no way to stop it. So if on the HQ router we get into privilege exec global config interface Ethernet 00 and say shut, and then quickly go back to the branch router, let's see. Yeah, and it went too quick, so let's do that again. I'm going to have to up the number here. So we're going to say, and actually before we say no shut, if on the branch router I say do show IP route EIGRP, now that was what you just saw right there was the syslog message indicating, hey, the adjacency is down. But that is because 3 hellos, or the hold timer, expired, right? 3 consecutive hellos were missed. The hello timer expired. The adjacency went down. But you'll notice that we don't see any dropped ping packets here, right? Or at least I didn't see any when we floated by. Yeah, no drop ping packets. And now take a look at what has happened. Who is the successor now? Exactly. WAN link 2, there is the computed distance, right? Not the feasible distance. That is the computed distance. There's the 2 computed distance values. But again, 2 was installed, and at the time we had run the show IP route EIGRP, it had only been in there for 4 seconds, right? So it basically swapped out the failed route with the feasible successor, and it did it almost instantaneously. So if I were to say do show IP EIGRP topology, you'll see that now we have and where is that path at? For right here is what we're looking at. You can see we have a single successor, right? So we have a single successor. And now we get down to what I was talking about earlier. And again, we don't have to really manipulate anything. Did that successor route have to transition into an active state? And the answer is no, because we already had a feasible successor. So we had a backup there. So it stayed passive the entire time. And here is proof. Again, remember, the feasible distance is calculated and is a static value. And that's why I was saying that it's not the feasible distance that's being reported here. This is proof that that's the case. Is that equal to what it says the feasible distance is right now? No, it's not. It's not. And we also know that this successor route did not go into the active state because here is the computed distance value and here is the feasible distance value, proving that that will remain a static value until and if and when this successor route transitions from passive to active and then back to passive. And I say transitions from because it's in passive right now. So it would have to go into the active state, then back into the passive state for that value to change. Remember, that is a snapshot, point in time value of what the feasible distance was when it was initially calculated. But we've had a change here. The successor, right? It says we have one successor. The successor is WAN link 2. When the successor was WAN link 1, the feasible distance matched up with the computed distance of the current successor. But now we have a new successor. Are there any feasible successors here? For that successor route, do we have any feasible successors? And the answer is no. There is nobody else right now who meets the feasibility condition. And we know who the other guy is, right? We know it's WAN link 3, and we've seen the epically large value that the reported distance is coming in as. It doesn't meet the feasibility condition. So remember, the first via statement, that is my successor, right? If there was another via statement, which we saw earlier up here, that would be the second and subsequent entries. Those are my feasible successors. But we have no one left who's going to meet the feasibility condition at this point. And we know that to be the case because we've already seen what WAN link 3 looks like. We know that there's no way that that value with 256.0.0.0.0.0 is going to be less than the feasible distance value of the current successor, right? So again, you can see that is the computed distance. And that is what shows up here. That is not the feasible distance. I can't stress that enough, again, because there's so much confusion about what the feasible distance value is in a lot of the documentation, that when learners then see this, the first thing they ask is, well, wait a second, the feasible distance here says 166,400, or what is that, 1664000, but over here it says 409600. I don't understand why the feasible distance here is different than the feasible distance here, and it's because this is not the feasible distance. That is not the feasible distance. Okay, so what we were going to try to do here is on the HQ router, we're going to say no shut. And so we're going to bring things back up. So let's check. Did that put it into active? Did that force that route into active? So we get a new neighbor that comes up. And what do you think? So again, it's installed back into the table, right into the topology table. And you can see that the computed distance is the same in this case. So we're back to our original topology. So what we're going to do now is, again, I'm going to bring that ping command back up, and I'm going to put a couple extra zeros on the end, and we're going to see how quickly we can make this happen to try to show that, come on now, and then shut this interface down. There we go. Okay, and that's what we're looking for. So we shut the interface down, and we have some packets that are being dropped. 1, 2, 3, 4, 5, 6. So it looks like 6, 2 seconds each, and then it dropped out. But it reinstalled that route into the topology table and everything continues to flow, right? Everything continues to flow. All right, let's make sure we've got everything covered here. All right. So with that link shut down, we already looked at the fact that the topology table changed. We didn't see another feasible successor in there. So we're going to let that continue. Now we're going to shut down interface Ethernet 02. So interface, and this, I believe, is what the problem was. So with that continuous ping running, there we go. Everything is just going to run really, really slow here. So we'll get back over here, and then, yeah, so now we're getting all these commands back. So interface Ethernet 01. Yeah, so the ping is still going, and this is what we're hoping to see here. There we go, and all we want to say is shut. And then we want to go back, and we want to look here at the ping. So the pings are going, and we're going to know when we shut that interface down, because we should see, and again, we're still waiting for that. Okay, there we go. The interface is down. And then there you go. There where the packet drops. And then immediately it installs that, the final route. I don't want to say the feasible successor because it wasn't, right? So Control-Shift-6, let's kill that. So do show IP EIGRP topology. And now what do we have? Who is the successor now? And again, we're kind of down, we're scraping the bottom of the barrel here from a path perspective, because two of our paths are down. We are down to the last and only remaining path. And let me ask you, did that route go into the active state? In other words, did dual have to run and recompute the composite metric in order to make a determination as to which route is the best? And it did. And it has to, because when we took link 1 down, it did not have to do that because there was a feasible successor. As soon as I took down link 2, meaning the first link and the second link were both down, we saw that prior to taking the second link down, there was no feasible successor, because this guy right here, based off of that reported distance value right there, did not meet the feasibility condition. Therefore, he was not in the EIGRP topology table as a feasible successor. He was in the topology table, just not as a feasible successor. So the first link was down, the second link goes down, and then what happens is that successor route has to go into the active state so that EIGRP can recalculate its composite metric to determine what route is now going to be my best route. And this successor, the only guy left, WAN link 3, gets chosen. But it has to go into the active state to do that, because based off of these metrics, right, the computed distance and the reported distance, based off the reported distance, the branch router cannot mathematically guarantee that this path via that successor doesn't loop all the way back around through the branch router and then make its way over to the headquarters router. Because again, that number is larger than what the feasible distance was before the WAN link 2 was taken down. And again, all very critical concepts. And so to kind of stress here, or to give you an idea, I'm sorry, I've got it right here actually. So this is the gentleman, J.J. Garcia Lunas Aceves, who came up with the idea of the diffusing update algorithm. And interesting, I didn't see that he worked at Cisco here, so I believe that he was doing this work on his own. And he is sort of like the Michael Jordan, if you read through this here. He is literally the Michael Jordan of computer science. And just a brilliant genius, right? Teaches at the University of California, Santa Cruz. And if I were to pull up real briefly here. Here was the first paper that he wrote, a unified approach, or the first one that I've been able to find, about distance vector or link states. And so if you come down, you can see this was written in 1989. And actually cost $1.50. But the paper was written in 1989. If I were to search for dual, it was initially called the distributed update algorithm. And again, these papers are fantastic to read to sort of understand the thinking at the time. And these two papers, this paper here and then the second one written in 93, talked about diffusing calculations. And if we search for dual again, you can see there is dual, right? And it's discussed. And this is where it kind of gets far outside of anything I think I will probably ever understand. But these are sort of the equations that mathematically prove that feasibility condition and prove that the feasible successor can be installed into that EIGRP topology table and provide you with a loop-free backup that it's mathematically guaranteed will not cause a loop in your topology. All right. Well, this is definitely going to wrap up discovery activity number 3. And I know we went a little deeper in some of the topics, but again, when we talk about the topology table, we talk about the feasible successor, the computed distance, the feasible distance, the reported distance, the feasibility condition. These things can become overwhelming. So it's very important that we stop, take time to break them down, talk about why the values are important, where you can find those values, and what those values mean to EIGRP. And this was one of the reasons why EIGRP initially had a significant advantage over other routing protocols, was because it kind of, and I'll use the word cheated, right? It kind of cheated by putting this feasible successor into the topology table. It really shortened the amount of time that traffic would be dropped, right? And of course, OSPF did catch up. They kind of came up with their, I think it's called fast reroute, or FRR, where OSPF said, oh, well, hold on a second. We can also compute a loop-free path and then kind of hold that as a backup in our back pocket, so in case the primary path goes down, we have a backup path. But again, hopefully you guys have a better understanding now of all of those values that we talk about with EIGRP, and when, why, how, what, and where you would expect to find them. All right, thanks so much for watching, and I will see you guys tomorrow night at 6 o'clock. Enjoy the rest of your weekend.